So far, we've looked at the derivative as being a rate of change in y and x. So we've been looking at gradients of certain curves. What we can also do is when we're looking at writing an equation with respect to time, so we're looking at how something is changing with time, then when we work out the derivative, it becomes a rate of change. So say, for example, if we graph the distance compared to time, then that would be a calculation of speed. So when we're looking at rates of change, we're really looking at sort of like the speed of something happening. That's pretty much what we're doing. So we can talk about an average rate of change, or we can also talk about the instantaneous rate of change. So an average rate of change is saying what is the speed that something's changing at if they were traveling the same speed or like the rate was the same the whole way through. So say, for example, if I was at school and I wanted to drive to UNSW, I could work out that my average speed would be, say, for example, about 40 kilometers an hour. So what I would do there is I'd work out what time I started, what time I finished, and I'm going to take the distance I traveled divided by the total time that I traveled for. But that's not a very clear indicator of what my speed was during my journey. So say, for example, I drive out of the school and then I drive down to Anzac Parade and then I stop at a traffic light. So when I stop at the traffic light, then my rate of change at that point in time is actually 0. If I've gone out onto Anzac Parade, say for example, if there's not a lot of cars that day, then I could be traveling up to 60 kilometers an hour if I wanted to. So my rate of change is different at all different times during that journey. So sometimes I'm faster, sometimes I'm slower. So sometimes we need to know what what is it at that particular moment. But there are also situations where we only need to know what the average was. So if I were going from Sydney to Melbourne, then I might want to know what my average speed is. So if I was traveling the same speed the whole way from beginning to end, what speed was I traveling at? I'm not as fussed about what my speed at, if I was 50 kilometers out of Sydney or 120 kilometers out of Sydney. I'm not really worried about what my speed was at that particular point in time. I just wanted to know if I was traveling the same distance, same speed the whole way through, what would that be? So both of these calculations are going to be really important for us. When we're looking for an average rate of change, so say for example, I've got this diagram here. So that's going to be a graph of a particular journey. So what we've got is time is along the horizontal, and we always talk about time being positive, because if we're talking about negative time, we're actually going back in time. So it doesn't make as much sense if we're trying to work out what's happening in the future. And then what we have is on the vertical, we're going to have some sort of quantity. Okay, so I've used Q for quantity. If I want to find the average rate of change, so I've picked 2 points here, so from here to this point here, so across this amount of time, then the amount of this substance is increased by that much. If I want to find the average rate of change, I want to find what the gradient of that chord is. So of that straight line, what is the gradient? So that will give me the average rate. So you can see that's a gradient formula. Okay, Q2 minus Q1 over T2 minus T1. Well, that's sort of like if we were to draw in a right-angled triangle, there's T2 minus T1, and that's Q2 minus Q1, vertical. So rise over run will give you Q2 minus Q1 over T2 minus T1. If I want to know the instantaneous rate of change, so say for example, if I want to know the instantaneous rate of change at T equals to 1, what I'm trying to work out is how fast is that quantity changing at that particular point in time? And that's when we're looking at the tangent at that point. So at that point, you can see that the gradient, rise over run, is much smaller than the average rate. So initially, it's growing quite slowly, and you can see that in the flatness of the curve, but then as time passes, it's growing faster and faster. So to work out the instantaneous rate of change, you're looking for the gradient of the tangent at that particular point. So what we're looking for is the value of dq dt when we have that particular time. So what we need to do there is we're going to differentiate q and then substitute the time in. So here's an example. The number of bacteria in a culture increases according to this formula. So B is 2t to the power of 4 minus t squared plus 2000, where t is the time in hours and b is the number of bacteria. The first question is to find the average rate of increase in the bacteria in the third hour. Now, be very careful with the terminology. If I'm looking at the third hour, so if I draw up just a really quick table, 0, 1, 2, 3, 4, 5, for example, then the first hour is between 0 and 1. Well, actually, I don't need a table, do I? Let me get rid of the table. So the first hour is between 0 and 1. The second hour is between 1 and 2. And the third hour is between 2 and 3. So when we're looking for this average rate, we're finding the gradient between the second and the third hour. And I've given you that as a hint. You're not always going to get that hint, so you need to make sure that you read the question carefully. So what we need to do is we need to work out the bacteria at both of those times. So remember, we're coming up to this average rate of change. So instead of Q, we're using B. So we want B2 minus, because we're using times 2 and 3. We want the bacteria at time 3 minus the bacteria at time 2 over the time at 3 over the time at 2. So that's what we need to work out. So when t is equal to 2, we're going to work out the amount of the bacteria. So that's 2 times 2 to the 4 minus 2 squared plus 2000. So put that into your calculator. That's 4 plus 2000. That's 2028. When time is 3, we're going to work out the bacteria at that time. So it's 2 times 3 to the power of 4 minus 3 squared plus 2000. So 2000, that's 2153. So we've worked out the rise values. Okay, the rise is going to be the difference between those two numbers, and the run values are going to be the difference between these two. So the average rate is going to be 2153 minus 2028 over 3 minus 2. So 3 minus 2 is just 1, so we just need to work out the difference in the first two numbers, and that's 125. So over that third hour, the average rate, we've increased by 125 bacteria in that hour. For part B, find the rate of increase in the bacteria at t equals to 3. So when it says at t equals 3, it means that we want the instantaneous. Okay, so instantaneous rate of change. So what we're saying is at that particular point, as soon as it hits the third hour, we're looking at the bacteria and counting how many bacteria have just popped up. Okay, how many new bacteria have just popped up. So to work out the instantaneous rate of change, we need to first differentiate. Okay, so remember we're differentiating and we're putting in time is equal to 3. So when I differentiate this, now because we're using different letters here, we're not using x and y, the better form to write it in is using the d notation. So we know what variables we've differentiated. So because it's b with respect to time, that's written as dB dt. Okay, if you were to use b dash, we won't mark you wrong for that, but often it's just nicer to write it in this format so you can see what variables you're comparing to each other. So when we go to differentiate this, we've got 2 times 4t cubed minus 2t, and then the 2000 just disappears. So that's 8t cubed minus 2t. So that's the derivative of the number of bacteria. So this will give us the rate of change. So when t equals 3, we want to work out what dB dt is. So that's going to be 8 times 3 cubed minus 2 times 3. So then put that in your calculator, and we get 210. So at that particular point in time, the number of bacteria is increasing by 210 bacteria per hour at that particular moment. Now you can see the average rate was 125 between 2 and 3. So what that means is the gradient in there is going to be 125. So if I draw in a little, let's draw in a little diagram. So it would be like saying if that's 2 and 3, okay, the gradient of that line is going to be 125, but when we get to 3, the number of bacteria is increasing at a much faster rate. So it sort of gives you an idea of initially it was probably increasing slowly, and then it started to get faster. Okay, last example here. So solve dB dt equals to 0. What is the significance of this answer? So we've already worked out the derivative up here, so we're going to substitute in dB dt is 0. So what we've got is 8t cubed minus 2t equals 0, and we want to solve this. Now, first thing to note is you do have common factors, so let's take those out first. So 2t is common, so 4t squared minus 1 equals 0. Now we've got the product of two items, so what we can now do is we can split it, kind of like you're solving quadratics. So we've got 2t equals 0, or 4t squared equals 1. Oh, 4t squared minus 1. Let's just do it one step at a time. Minus 1 equals 0. So on the left, we have t equals 0. That's one solution. And then if I've got 4t squared minus 1 is 0, then t squared is equal to a quarter. So what I did was I added the 1 across, then divided by 4. So then t is going to be plus or minus a half. So we've got three solutions there. So therefore, t equals to negative a half, 0, and a half. Now, since t is a positive value, we're going to ignore the negative half. So, but since t is greater than or equal to 0, then t equals to 0 and a half. Now, we need to work out what does this mean about the graph. When we solved that the gradient was equal to 0, what we knew was that the tangent was horizontal. So what this means is at these 2 points, at 0 and a half, what would probably have happened is this graph would have come up, it would have gone flat, and it might be coming back down. Or it might have gone down, it's gone flat, and it's coming back up. So at this particular point, that's what we're actually trying to model. So what we can say about these two values is that when we get to t equals 0 and t equals to half, the rate of change is equal to 0. And if the rate of change is 0, then the number of bacteria isn't increasing and it's not decreasing either. And that only happens at that specific moment. So as soon as you pass over the half, or as soon as you pass over 1, then the number of bacteria starts increasing or decreasing again. So what we can say there is that the significance of that is at t equals 0 and a half, let me just wipe off these, the number of bacteria isn't increasing or decreasing. Now, a really important word that we use for that is we say that it's stationary. Stationary. Now, it's stationary with an A, okay, A there. If you use E, that's actually like, your stationary, as in like your pens and pencils, okay? So if you use an E, it means your pens and pencils. Station A, airy, is that the object has stopped. Just quickly going over a bit of terminology. So based on this, we've talked about dB dt equal to 0, and we've also worked out rates of increase as well. If we're looking at a particular graph, we can say that the values are, like, the graph is increasing or decreasing. So increasing meaning there's a positive gradient, decreasing means that it's got a negative gradient, or it could be stationary. So things that you're looking for is if the gradient is positive, so if f dash a is greater than 0, then the curve is increasing at that point. If the gradient is negative, then the curve is going to be decreasing. And if the gradient is equal to 0, then we have the graph is stationary. So it's not going up or it's not going down either. So if we could have a go at a couple of these questions. Next lesson, we're going to take this idea of increasing, decreasing, and stationary and actually further develop it into graphs. But just start with these questions for now, and then we'll do the next part next lesson.